So we're going to talk about the graphs of rational functions. Um, so we're looking at functions that look like this: p of x divided by q of x. And in this function f of x, we're going to have p of x and q of x are both polynomial functions. And one thing that makes these graphs kind of weird is that so one thing that makes these graphs weird is that we can have points where the graph is not defined. So we know division is not defined whenever the denominator is 0. So we can't have, since q of x is the denominator, so f of x will not be defined whenever q of x equals 0. So that's another way of saying any x value that makes the denominator 0 will not be defined. So what happens is we're going to have like single x values on this graph or on these graphs where the function's not defined. So up until now, all the functions we've looked at are continuous functions. A continuous function is a simple way to say it. A simple way to say it is entire function is continuous if the entire function can be drawn without lifting your pencil or pen or whatever. So for example, this completely made up function that I'm about to draw is continuous because I drew the entire thing without having to pick up my pen. Whereas a function that looks like this, and this is not a function that we'll deal with in this class, but if you had a function like that, so notice how I put a closed circle here and an open circle here. So it's one function, but it has two parts because from when I get to here, it jumps down here, right? So this function is not continuous. All right, so let's look at some graphs now. So we said division is not defined when the denominator is 0. So this is a function we've already looked at. This is 1 over x. As you can see, it has an asymptote when x equals 0. If I change the denominator to be x minus 1, then now it's not defined at x equals 1. It has an asymptote of x equals 1. So let's say I leave the x minus 1 in the denominator, and now I also put x minus 4 in the denominator. So let's think about this. It's still going to be undefined when x is 1, because that makes the denominator 0. It's also going to be undefined at 4. And the graph looks like that. So it almost looks like it's 3 different functions, but it's all one function. The asymptotes are these blue vertical lines. So it's all one function, but it has 3 parts because it has 3 discontinuities. So when you get to x equals 1, the graph goes up forever, but it never reaches that blue line, and then it reappears back down here on the other side of the blue line, but still never touching it. So this is one graph that has 2 vertical asymptotes. And you can go crazy here and add as many asymptotes as you want. So now I put one at x equals 3. So we have another asymptote at x equals 3. So now again, it looks like the graph is 4 parts, or it looks like the graph is 4 different functions, but it's actually just one function broken into 4 parts. So it goes like that, and then down, reappears on this side of the asymptote, goes down, and then up, and then you have to jump down here, and then you jump back up here. So from this, we can see we will have a vertical asymptote. So if q of x equals 0, we have a vertical asymptote. So for example, if I make up a function here, so let's do 1 over x minus 3 times x plus 2, then this function would have vertical asymptotes, and I usually abbreviate that as VA. So it has vertical asymptotes at x equals 3 and x equals -2, because both of those numbers would make the denominator 0, and we can't divide by 0. All right, so now we're going to think about what happens if the numerator is 0. So we're going to get rid of all this. Now, suppose I have the function x over x plus 1. So we know if the denominator is 0, then we get an asymptote. The numerator is 0, well then think of a division problem where 0 divided by a number. You have 0 cookies and 20 people in a room. Each person is going to get 0 cookies. It's defined. It's not a silly question. So what happens if this function, if x equals 0, then you get a 0, or an x-intercept when x is 0. And if I change the numerator to x minus 1, then now I have an x-intercept at x equals 1. Or if I change the numerator to x minus 9, then all the way over here, it equals 0 when x is 9. And if I put more than one factor here, so x minus 1 and x plus 2, now I have zeros at -2, positive 1, and still I have an asymptote at x equals -1, right? So now we can see if, so we have zeros, and zeros is another way of saying x-intercept. So we get zeros when p of x equals 0. So for example, the function, and remember p of x is just numerator, whatever function is in the numerator. So if I have some made up function g of x equals x minus 3 times x plus 1 over x minus 12, then this function would have x-intercepts at x equals 3 and x equals -1, and also would have a vertical asymptote at x equals 12. So we've covered when the numerator is 0 and when the denominator is 0. The next question is, what if they're both 0 at the same time? So let's think about a function like this. So according to what we have so far, this would have a 0 when x is 1 because of the x minus 1 factor in the numerator, and an asymptote at x equals 1 because of the x minus 1 factor in the denominator. But obviously it can't have both of those things at the same time. Additionally, if we look at this algebraically, the factor x minus 1 is common to the numerator denominator, so it really should cancel out, right? And it would look like, if you cancel those out, you end up with just x plus 2. And sure enough, that's what the graph looks like. We have, that just looks like the straight line x plus 2. And you can see they're the same thing. But there's one thing that's different about this graph. Because we know division by 0 is not defined. If I go to the point where x is 1, I'm undefined at a single point on the graph. So that's called a hole in the graph, right? And if I also put x plus 2 in the denominator, so now the whole thing divides to 1. So it just looks like y equals 1, the straight line, but it has a hole here at x equals 1, and a hole here at x equals negative 2. So we get a hole in the graph if p of x and q of x are both 0 for the same x value. So again, I'll make up a function. So I have x minus 2 times x plus 3 divided by x plus 3. This graph would have a hole at x equals negative 3, because that's the factor that would divide to 1 here. And also, the graph would look like so it would look like the function y equals x minus 2. Because after you divide this part to 1, you're just left with x minus 2. All right, so the last thing we're talking about is horizontal asymptotes. So when we talk about horizontal asymptotes, what we really want to know is what happens to y as x goes to positive or negative infinity. So that's the furthest right or the furthest left on the graph. I want to know what happens to the y values when I go all the way to the right or all the way to the left in a graph. So let's compare a couple of graphs here. Say we have, start with 1 over x, right? So as we go way out this way, we can see this gets closer and closer to 0, but it never quite gets there. And this makes sense, because if we were to evaluate the function at these x values, 1 divided by 300 is a very small number, right? 0.003. But no x value would ever get this to 0, so it has a horizontal asymptote. But now, what if I change the numerator? So if I let's make the denominator x squared, and change the numerator to x minus 1. Sure. So now, even though So the numerator gets bigger as I go this way, but the denominator is x squared, and x squared increases much more quickly than just x minus 1. It even increases more quickly than 10x and plus 100, or 100x plus 100. So if I go far enough out, you can see that eventually the numbers here are much bigger than the numbers in the numerator. So since the denominator is much bigger, the y values are going to 0, right? Or say I change the numerator to have a squared now, but in the denominator I put a cubed. Still, the denominator is growing quickly, so the function ends up going to 0, right? So let's go ahead and write that down. So what matters here is we're looking at the degree of each of those functions. So let's remember degree is the highest exponent. So if the degree of the denominator is bigger, then we get a horizontal asymptote at y equals 0. So then it would make sense. So if the degree of the numerator is bigger, so if I just switch these two things around, 100x squared plus 100 and x cubed. So x cubed is bigger than 100x squared plus 100. So what do we see towards the end? The numbers are getting bigger. So even though this is going to go very, very slowly, the numbers in the numerator are increasing much more quickly than the numbers in the denominator. So this function does not have an asymptote. It just keeps going and going and going. Bigger, bigger, still bigger. Going slowly, but they're getting bigger. More exaggerated if I make this just x squared. Then you can see this function shoots off to infinity in both directions. And if you go to the left, same thing. The y values keep getting more and more negative, and they never come back down to 0. So if the degree of the numerator is bigger, then there is no horizontal asymptote. So now there's one other question. What if they're the same? So let's go with x cubed plus 1 over x cubed minus 4x plus 10, whatever. So we're looking at y values as x goes to infinity. So we go farther and farther and farther out. And what do we see? Well, the y values are getting very, very close to 1. Not exactly 1, but very, very close. See, 1.0001. So let's look at a few other options. Let's change the x cubed to a 3x cubed. So now it looks like the y values are going to 3. Okay, now let's change the denominator to 2x cubed. Now the y values are going to 1.5. Are we starting to see a pattern? Let's change it to a 4. The y values are getting very close to 0.75. if I change this to 12, now the y values are going to 3 again. So hopefully you picked up the pattern that the asymptote, the number the y values are approaching as we go this way or this way, is whatever the leading, so you divide the leading coefficients. So it's the ratio of leading coefficients. So what happens is that these other numbers at the end become inconsequential because they're much smaller than, so even when I add other things, plus 90x, it's still, when you get to really large y values, or really large x values, then these other numbers in the denominator don't matter. So it's just, all that matters is these leading coefficients. 20. So 20 divided by 4 is 5. So if the degree is the same, then it's the ratio of leading coefficients. So in all the practice problems that you're going to get about these functions, the sad thing is, once it's in this form, you know what the answers are. The sad part is, usually you have to factor it first, so then you can see what all these things are. Of all 4 of these, remember, horizontal asymptotes do not rely on factoring, because all you have to do is look at that first term, right? So looking back at one of our previous functions, if I wanted to know the horizontal asymptote of, let's go with this function here, g of x, I would actually have to multiply it out. So in the denominator we have x, just one x. In the numerator we would get an x squared. So g of x here would not have a horizontal asymptote. Whereas in this function, so in my vertical asymptote box, this is a 1 and it's divided by x minus 3 and x plus 2. So this one would have a horizontal asymptote of y equals 0. And again, in this one, since I have x squared in the numerator and only x in the denominator, this would not have a horizontal asymptote. So remember, when you're asked for all this information from a function, before you factor it, you can get all the horizontal asymptotes. Then you factor it and you deal with these other 3 boxes.